Oh man. Welcome to those at home. There's only 4 in the audience here for this lecture. And the reason I sound funny is not because I'm about to die of a virus, but because I'm going to die from pollen, and I've got an allergy. And hopefully create some stress. Stress, I found, is the only thing that cures me. If something, maybe having to meet somebody I don't want to meet, or something, going to the gym with some awful weights, then that cures me. But this isn't stressful enough, so you've got to be annoying, okay? Just do your best. Okay, so first of all, we'll call HMMs. So we have just a controlled Markov chain, all the same notation, no changes whatsoever, but then we have observations. And it's assumed that, well, I'll write it out in this sort of explicit way. Yeah. I'll write it like this. Basically, if the controlled Markov chain, that means it can be expressed in this way. And the observations are some noisy function of the state. Okay? And from this, we can get this we can get this conditional distribution. So x is, I'm assuming x here is on a discrete state space, and we can work out the conditional probability that xn equals x given observations up to time n. And that's a hidden Markov model, and that's one theory. So this comes up in communications, all sorts of places where there's no control at all. You basically just want to estimate a state, and that's it. And then you get to POM-DPs, where you want to have un as some feedback law that depends on y0 to yn. And last lecture is like my favorite lecture in a way of the whole course. Not last lecture. No, last lecture wasn't a lecture. Last lecture I just dropped in discussion on reinforcement learning, so we'd all know what I'm talking about when I say reinforcement learning. So when I say last lecture, I'm referring to just before spring break. We start with something that looks completely intractable. I mean, imagine how hard, anybody even having the bravery to consider this problem of optimizing overall feedback laws for a discounted or average cost optimal control, or finite horizon anything, it took some real guts, and eventually it was discovered that there's a sufficient statistic, and the optimal policy is actually some gigantic stationary policy, just a function of Bn. This is true for, say, for average cost or discounted cost. When you come to finite horizon problems, the policy is no longer time invariant, because it's based on the cost to go and all of that. So for these infinite horizon problems, you get that the optimal policy is just a static function of the belief state. And see, that's why, to make things concrete, I'm sticking to a finite state space, so you can really think of Bn as a vector. X is like the index. X goes from the first state to the last state. So if there are d states, it's a d-dimensional column vector. And so you've just got this thing here, and that's it. So, and in my notes you'll say, I have some questions, and I say, Has anyone solved one of these things? And the answer is no, except for LQG. Okay, so if you have a linear system with, everything's linear with Gaussian noise, and if the observations are linear, Gaussian noise, and we've assumed throughout that these guys are independent. Then it turns out that this is Gaussian. It's a density now. It's no longer a probability mass function. But because the belief state is characterized by just two statistics, its mean, a conditional mean and conditional covariance, it's no longer infinite dimensional as it would be if you're just talking about densities. Imagine if you had to say, I want a feedback law that's a function of a density, but it's a Gaussian density, so all you need to know is its conditional mean and conditional covariance. You can work this out and you get something trivial. And I think I might make you do this, Joel. I might make you give the special case of, not today, don't worry, of LQG. But outside of that, I don't know of any other applications of this. So why on earth would I teach it? So the main motivation for teaching is not to learn about LQG. It's because this is the gold standard, and in practice we try to approximate it. So basically, we know that we optimally like to have some feedback law of this conditional distribution. What we're going to end up doing in practice is say, well, I don't know what the hell that is, but I bet I know what's important parts of that. Some conditional mean, conditional variance. And when people talk about features, that's at least in a statistical point of view, that's what they're talking about. So typically, we're going to look at hacks. Well, no, I shouldn't do that. I'll do this. I'm just going to, I'm going to leave it, You come up with some feature vector and chosen so that psi in is in yn for each n. And then first you use some intuition to define these guys, and then you go about some method to find the best feedback law of those features. And that was the point of last lecture, is that reinforcement learning is one way to do that. That you pretend that that's a belief state, and then you run some reinforcement learning algorithm to find the best feedback law in some sense, and sometimes that works really well. It surprises me how often that works. It blows my mind how often you can take some stupid features, use reinforcement learning, and you get a policy that works, and nobody knows why. Nobody knows why. Why you can get away with these things. Okay? Okay, cool. So, so the fact that, I didn't, basically what I, in the lecture before spring break, but the only thing I blew off is I didn't derive the filter for you. I did sort of quickly, it's so boring. It's Bayes rule and a bunch of annoying notation. It's awful. So you don't need to know the derivation. It's pretty intuitive once you write it down. I'm not gonna write it down again, but that's that. Before I go on, let's see, what else? Look at my notes. Oh yeah. Oh yeah, one note. In the homework, or assignment 6, it doesn't look like this. And you might look at that and say, well, you're cheating, Professor Mine. That's not right. The observation is supposed to be a function of the state and noise. And there's two ways you can deal with this. One is you can just rederive the filter. It's trivial. Having the observations depend on this and this. If you just go through step by step and look at the derivation, Bayes rule, you get the filter is barely changed. Okay. But one approach you can use is you can say phi k equals xk uk minus 1 is itself a controlled Markov chain. You know, so, you know, because at time k, would you all agree that xk, we said, I mean xk plus 1, you know, is a function of, yeah, the input uk, it's still the input, and only xk. So it's not a function of phi k, because if it was, there'd be a uk minus 1 in there. But functions can eliminate variables. That's what we were discussing on Tuesday. So the xk evolution is the same. And phi k plus 1 has uk. Well, that certainly is a function of uk. All right, phi k plus 1, its lower component is uk. I would say that uk is a function of uk, right? So this can also be written in a similar form as that. So you can actually just say that's the state, and write down what the resulting filter is. Okay. But I think you should just go and rederive it. It's instructive, just to make sure you understand it. Bayes' rule, you're done. All right. So here's an application. And this is a huge field. It's multi-arm bandits. And I really encourage you to look at that. Did you all see that I broadcast a tutorial by Chaba? He's at DeepMind. And has been in this area forever. He wrote the first really beautiful analysis of sort of convergence rates for Q-learning, for Watkins algorithm. So you know, if you want to know more about that, look at that. I mean, I'm going to give you a very, very brief introduction. But the bandits, I mean, you know, obviously the language sounds like you're talking about slot machines, you know. It's not very useful there because everyone knows that you're going to go broke. So you're not going to try to optimize, because the optimal strategy is to go away, get the free drinks and leave. But it's big. Biggest probably is in advertising. You know, pulling an arm. In the multi bandits are slot machines. You know, you pull arms, but in advertising, pulling an arm is just, I've got a budget. Every dollar I spend is like one arm pull, and I decide to put up a billboard here or pull up a billboard there. You know, that's one bandit or another bandit, or I decide to put an advertisement in the New York Times or the New Yorker or whatever. Each one of them. You know, there's a different, there's a cost to pulling, and then there's a reward which is unknown. That's the main thing. It's huge. I mean, today, you know, especially in the web, for clicks. So, so there, you know, it's. Damn, this is gone. So here it's a little bit confusing, because if I'm looking at the web, I click something, it sounds like I'm pulling an arm and hoping to see something fantastic. Well, not at all. It's sort of I want to sell a product, so it's really an advertising again, and I'm going to pay to have some button visible to the users, and every time every time somebody clicks, Google makes some money, and I potentially make some money. So Google's reward is clear, and they hope to maximize the number of clicks. And me, as somebody trying to sell a product, I have to decide where I'm going to put these potential clicks, this bait, based on a cost for doing it and a very unexpected reward. I have no idea how much revenue I will make from the advertising. Let me say, I wrote down a list. There's, and then in stocks, in finance. I mean, so I think that probably in finance, so before this golden age, in quotes, of the internet, I think the first thing people mention is finance. That an ARM is a stock. I put $1 in a stock, and the next day I look at it, and the reward is uncertain. Okay. All right. So these are applications, and here's the controlled Markov chain model that captures this. So let's just look at a 2-arm bandit. Okay, you're going to see right away that I really don't capture everything in these applications. But what I'm going to say for the 2-arm bandit can be extended to things I'm missing. We'll talk about what we're missing in a moment. So let me just make it completely abstract and then explain it. So I've got a Markov chain. xk is in R plus 2, so it's a 2-dimensional vector. And I'm going to forget about the finite state space. It doesn't matter. It just doesn't, it's irrelevant. So it's that. And it's got some really exotic dynamics, okay? So it's fairly stable. Whoa. It's MM1Q with complete abandonment, I don't know, and no input. So basically, what this is that it's just a static reward. I mean, this is sort of the reward. It's a static thing that never changes. You know, so it's a very, very special case. And when I say more, it'll be clear what I'm doing. And then I've got, so that's my state dynamics. It's definitely this form, right? And then there's a actions. So the whole point is that one of these guys, is bigger than the other, you know. And actually, in the end, it's going to be. You'll see why. I'm going to change the notation in a bit. M1 and M2. Maybe it should be. You'll see why. And then what's the observations? Basically, pulling an arm means I get to observe a noisy version of this. So if, say, if action U, if let's say action UK is 1, or I'll just say that, or 2. And so put it like this. How do I say this? So, so that YT, it actually turns out our observations are really of this form. So YT is going to be equal to just this X0. Let's see, how do I say this? Well, I write it like this. I wrote T here, and then to keep it as K. Okay, let's just stare at this for a bit. And so this is additive noise here. So W, the noise appearing here is also two-dimensional. And we'll assume it has zero mean. So we have noisy observations of these means. And so all right, cool. So basically, if you look at the tutorials that I sent out and things like that, you'll find I'm changing things a little bit to force it into the framework of this. You know, and we can now solve this, right? I mean, what could be more trivial? I have to give you an objective. I want to maximize the reward. So basically, typically, you look at this as a finite horizon problem. So you just basically, what you want to do is you want to I should say here, every time I pull the arm, I also, not only do I observe this quantity, I get to eat it. I get this money in my pocket, in a sense. That's how I'm going to set this up. So, yeah.
For you, 1 and 2. So if the user, whatever, chose 1, then they would get some two-dimensional Gaussian shape.
Yeah, no, I mean, well, no, W could be uniform. It could be anything.
Two-dimensional noise added to.
Yeah, there's a noisy, because the point is that I don't get to see. I mean.
You don't have first state x0, but that's never changing. All this.
Yeah, that's just a joke. It's just to make it fit into this in this model. So this xki is really just mi. It's just some number. You know, I mean, we can put typically you do put a distribution on this. That's the Bayesian setting. Okay, so we'll talk about that in a minute. But the point is. If I'm trying to sell some expensive sweater, advertising on Facebook, right? Or not sweater, I mean clothing, right? People are going to click, and some people are just going to go and buy the cheap socks that I have on sale, right? And and other richer people are going to buy the cashmere sweaters, a bunch of them to give to presents to all their kids. And so every purchase is a different reward to me, and that's what these are, you know. So there's some mean value, which is if I kept this going for a whole year, how much would the average revenue be per person, right? But the volatility of each purchase, which is given right there, is, you know, could be very high.
And so that volatility is what the noise, that W.
It's meant to model that, the fact that not everybody buys the same thing, you know. They're all spending different amounts of money. That's the most concrete, yeah.
And so the I here refers to the component of the vector, though.
Yeah, which one? Yeah, so basically, so in the case of selling clothing, I've got, and by the way, notice that I'm ignoring the costs. So basically, the only way that's justifiable if I'm advertising, say, in 2 different magazines, and they both charge the same amount, so I can get that out of the picture, you know. Or I could subtract things off, but anyway. Forget about the cost of advertising. I want to find out if I will make more money advertising in the New Yorker versus the New York Times. And it's going to take me a long time to learn that. All right? And so I'm going to have these observations, and eventually I'll decide that, hey, the New York Times sucks. I'm going to stick with the New Yorker. Yeah. Okay, cool. And so what you want to do, I mean, basically you can start off by saying, I want to maximize yk. Now that looks crazy at first. Maybe or maybe not. Well, actually, based on my description, that's what you really care about. But you can boil this down to something more similar to what's in the course. So this is what you really care about based on my description. But then we can go through and write this out as the expectation of one sum. If this one's okay. Yeah, this pen will work. So I did two things here. I mean, first of all, I broke up yk into the two possibilities. You know, the previous input could have been 1 or 2, right? And then y is the sum of two terms. But remember, these guys are supposed to be IID. And they're also assumed to be 0 mean. By the way, that's not a square. That's just the second component. Sorry. It looks like a square. And so basically, there should have been a plus wk1 here, but that's 0.
Is yk one-dimensional or two-dimensional?
Yk is one-dimensional. Have take a look. Yeah. All right, this is just a number, and that's just a number, so it's one-dimensional.
Okay, so...
Yeah, but there are two possibilities. I mean, I could have chosen previously 1, or I could have chosen 2.
I thought
and so,
before wk was in two-dimensional as well.
Yep, take a look. It's two-dimensional.
So the I is not picking, like, you don't have two
well,
distributions.
wk, I'll write it like this. Wk is equal to wk1, wk2. Okay.
Okay.
All right? Yeah. Yeah. So it's all good. And so yeah, I'm using the fact that wk is IID, so it's independent of anything in the past here. And so we've got that. So and yeah, that's a max. Yeah, that's clear. So I want to maximize that quantity, and you know, we have the theory, right? We can go through and we know the solution will be that u star k is going to be some phi of t minus k. If you go back and look at your notes of bk, happy phase. Yeah. And in that case, forget this last thing. Actually, forget it. Yeah, don't. This is non-Bayesian. Cross that out. Cross that out. I'm being stupid. That'll ruin the whole message I'm about to say. I'm not going to look at a deterministic initial condition. I'll be screwed. All right. This is random.